Hi everyone, and welcome back to Math Together Canada. Today, Kaylin will be solving questions 13 to 19 of the 2024 AMC 10B, a section where the problems get a lot more challenging. Let's dive into her solutions.
Now let's move on to problem 13. So the question says positive integers x and y satisfy the equation root x plus root y is equal to root 1183. What is the minimum possible value of x plus y? So first we can factor 1183. So the number is equal to 7 times 169, which is 13 squared. So root 1183 is equal to 13 root 7, right? So that means that is equal to root x plus root y. And because we want to minimize x plus y, that means that they're both going to be in the form a root 7. Over here, it's just the format. They don't have to be equal. So because x and y are both integers, that means that this has to be an integer for both of them. So the closest possible integers that add to 13 are 6 and 7. So that means that x and y are equal to 6 root 7 and 7 root 7. So the sum of x and y, or I guess roots, the sum of x and y are 36 plus 49 times 49. And this number is equal to 595, which is B. I'm gonna move this up. Okay. Next question, problem 14. A dartboard is the region B in the coordinate plane consisting of points x, y, such that the absolute value of x plus the absolute value of y is less than or equal to A. A target T is the region where a dart is thrown and lands at a random point in B. The probability that the dart lands in T can be expressed as what is m plus n. Okay, so I guess we can draw out this dartboard. So, this is the graph. It's basically a square with side length 8 root 2, and my drawing is very not accurate, but that's okay. So that's the dartboard, and we can first simplify what t is. So x squared plus y squared minus 25 squared is less than or equal to 49. So negative 7 is less than or equal to x squared plus y squared minus 25 is less than or equal to 7. So 18 is less than or equal to x squared plus y squared is less than or equal to 32. So these are two circles, and basically what we're finding is the region inside the bigger circle and outside the other, outside the smaller circle. So the areas are, so for x squared plus y squared is equal to 32, the radius is 4 root 2, and the area is 32 pi. And for the other one, the radius is 3 root 2 and the area is 18 pi. So that means that the area of T is 32 pi minus 18 pi, which is 14 pi. And the area of the square region is, so this is 8, this is 8, so the length is 8 root 2, so the area is 128. So simplifying, this is 7 pi over 64, and so that means that the value of m plus n is 7 plus 64, which is 71, which is B. Okay, so problem 15. A list of 9 real numbers consists of 1, 2.2, 3.2, 5.2, 6.2, and 7, as well as x, y, and z, with x is less than or equal to y is less than or equal to z. The range is 7, and the mean and median are both positive integers. How many ordered triples x, y, z are possible? So we can first deal with the mean condition. So the sum of the 6 numbers given is 24.8. So we can write that out. The sum is 24.8 plus x plus y plus z, which is 9 times an integer. Right. So the only possible values of x plus y plus z are going to be 2.2, 11.2, 20.2, and it can't be more than 20.2 because the range of the list is 7. So even if they were all greater than 7, there's the largest that z could be would be 8, and the sum would be less than 29.2. So those 3 values are the only possible values that x plus y plus z can be. And we can also rule out 2.2 because we see that one of x, y, and z has to be the median of the list because the numbers given to us right now are all not integers and the median has to be an integer. So we can rule out this case. So now x plus y plus z can only be 11.2 and 20.2. So let's consider the bigger case first. So case 1 is 20.2. So all integers, all of the 3 integers x, y, and z have to be less than or equal to 8. So x, y, z less than or equal to 8. And y and z also have to be on the bigger end of the list. So the median that we're looking for, which is one of x, y, and z, has to be between 5.2 and 6.2 because we're adding 2 more integers to this side. So that means that because the only integer between 5.2 and 6.2 is 6, that means that x, which is the median, has to be 6. And then now we can see that to make the range 7, that means that z would be 8. And finally, to make this sum 20.2, y would be 6.2. So this gives us one triple. I'll write it over here. So one possible triple is 6.6, 6.2, and 8. So now we can consider the second case, case 2, which is when x plus y plus z is equal to 11.2. So the average of x, y, and z has to be sort of, one of them has to be the median, and one is less than the median, and one is greater than the median because of the 6 numbers that were given already. So that means that y is the median, and x and z are on each half, one is on each half respectively. So then we know that the median has to be between 3.2 and 5.2 because 3.2 and 5.2 are number 3 and number 4 given to us right now, and we're adding one number to both sides. So that means that y is 4 or 5. So for each of these cases, we can find another triple. So when y is 4, x is 0.1, and z is 7.1. And when y is 5, x is 0, and z is 6.2. So that means that we have a total of 3 triples x, y, and z. So our answer is C. Okay. Moving on. Jerry likes to play with numbers. One day he wrote all of the integers from 1 to 2024 on the whiteboard. Then he repeatedly chose 4 numbers, erased them, and replaced them by either their sum or their product. After repeatedly performing this operation, Jerry noticed that all the remaining numbers on the whiteboard were odd. What is the maximum possible number of integers on the whiteboard at that time? So we see that we can replace all the odd numbers with 1 and all the even numbers with 0. And the conditions of adding and multiplying would still be true. So now we have 1012 ones and 1012 zeros. And we want to have all the numbers on the whiteboard be odd, so we want to get rid of all the zeros. So to do that, and we want to have a maximum possible number of integers remaining, we want to add or multiply groups of 4 zeros at a time. So basically, we start at 1012 zeros, and then we go to 253 by combining them in groups of 4. And then after that, we go to 63, which is 253 over 4 floored. And then we have another one over there. So that's 64. And then we go to 16, and then we go to 4. And then we go to 1. So now we have 1012 ones and 1 0. So to get rid of this final 0, we need to take 3 ones and add them. So from the 1012 ones, we're taking 3 and then combining it with this. So now we're getting an extra odd number 1. So we had 1009, and now we're adding 1 back. So the maximum possible number of integers after all the remaining numbers are odd is 1010, which is A. Okay. Next question. Problem 17. In a race among 5 snails, there is at most 1 tie, but that tie can involve any number of snails. For example, the result of the race might be that Dazzler is first, Abby, Cyrus, and Elroy are tied for second, and Bruna is fifth. How many different results of the race are possible? So we can sort of split this into cases, right? So if there are no ties, that's case 1, and there are just 5 factorial, which is 120 ways to order the snails. Then if there are 2 snails that are in a tie, then we have 5 choose 2 ways to choose those 2 snails, and then 4 times 3 factorial ways to order everyone else. So that is 240. And then for 3 snails, there are 5 choose 3 ways to pick the 3 snails, and then 3 places in the race to put the tie, and then 2 factorial ways to order the 2 remaining snails. So this is 60. And then when there's a tie with 4 snails, there's 5 choose 4 ways to pick the 4 snails, and then 2 places to put them, and then 1 way to put the remaining snail. So that is 10. And finally, when there are 5 snails in a tie, there's just 1 way to do that. So if we add everything up, then it's 120 plus 240 plus 60 plus 10 plus 1. And our answer is 431, which is D. Okay. Question 18. How many different remainders can result when the 100th power of an integer is divided by 125? So we can say n to be 100 is congruent to something mod 125, and we're looking for that something. So basically, what we see is that if n is a multiple of 5, then n to the 100 is going to be congruent to 0 mod 125, because we can write n as 5x, so then it would be 5 to the 100 times x to the 100, and that is a multiple of 125. So a possible remainder is just 0. And then we look at the case where n is not a multiple of 5. So n is relatively prime to 125. So by Euler's totient function, or theorem, I guess we can see that n to the 100 will be congruent to 1. Yeah. So that means that the two remainders can only be 0 and 1. So there are two different remainders. And then finally, for problem 19, in the following table, each question mark is to be replaced by possible or not possible to indicate whether a non-vertical line with the given slope can contain the given number of lattice points. How many of the 12 entries will be possible? So we can fill out this chart, I guess. So when the slope is 0, then y is equal to k will be the equation of the line. So 0 lattice points is definitely possible because, let's write the equation out here. So y is equal to k, and if k is not an integer, then every point on this line will not be a lattice point because the y-coordinate will not be an integer. So this is yes. And then for the next two, so exactly 1 and exactly 2, this is not possible. But the last one, more than 2, is possible. And for more than 2, we can have an example, so y is equal to 1. So 3 lattice points on this line are 0, 1, 1, 1, and 2, 1. So we can see that that is possible. But for exactly 1 and exactly 2, these are both not possible, because if, like, let's say that there's a lattice point AB on this line, then that means that the line equation has to be y is equal to b. But then a plus 1b and a minus 1b are both points on this line that are also lattice points. So, okay. So for the next one, non-zero rational slope. So 0 lattice points is possible because, let's say that the line has slope like p over q, for example, and I'm gonna write that over here. So y is equal to p over qx plus k. Right. So that means that if a line passes through like some sort of lattice point AB, then A is a multiple of Q. So we can have like multiples of A as X, and Y would still be an integer. So exactly 1 and exactly 2 are not they're not possible, but more than 2 is possible. And then for 0, we can see that like, for example, if we look at the line y is equal to x plus 1/2, for example, then none of the points will be lattice points, because if x is an integer, then y will not be an integer, and if y is an integer, then x will not be an integer. So 0 is possible. So for our last case, irrational slope, we can say that so let's say that the slope is like square root, or I guess, no, it doesn't have to be square root, but let's say that there are two lattice points, A, B, and C, D, for example. So then the slope would be D minus B over C minus A. And that would be rational. But over here, that's a contradiction because it says irrational slope. So that means that there cannot be exactly 2 or more than 2 points, lattice points. But there can be 0 and 1. So for 0, if we look, for 1, if we look at the line y is equal to root 2x, then when y is equal to 0 and x is equal to 0, this is a lattice point. And then, so we also see that 0 is possible for irrational slope, because if we look at the line y is equal to root 2x plus root 3, if x is an integer, then y is never going to be an integer. And if y is an integer, then x is never going to be an integer. So that gives us all of the question marks that we are looking for. Not question marks, sorry, check marks. So if we count them out, there are a total of 6, which is C. Okay.
And that wraps up questions 13 to 19. Definitely some tougher ones in there. Thanks for sticking with Kaylin through these challenging problems. Make sure to subscribe so you don't miss the final part, and let's finish the contest strong.